The notes for Unit 6, Lesson 6 will cover the ideal gas law. So this is the fifth law and the final law that we will cover this unit. So again, we have Boyle's law, Charles' law, Guy-Lussac's law. We have the combined gas law, and now we have the ideal gas law. So after these notes, you will be able to calculate any unknown variables when using the ideal gas law. So make sure you have your notes packet available and a calculator. All right, so the ideal gas law. So an ideal gas conforms precisely to all the assumptions of the kinetic theory. So ideal gases have gas particles that are in constant random motion. There's no attractive forces between the particles. We're assuming that every time these gas particles collide, their collisions are elastic, meaning that no energy is lost. So an ideal gas does not exist, but it's this set of standards that we can use to apply other gases to predict their behavior. So the ideal gas law is the only gas law that includes all four variables of the gas. So the ideal gas law equation is PV equals nRT. So sometimes you'll hear me say PIV nRT. So PV is equal to nRT. And then underneath we have what all the variables represent. So P is pressure, V is volume, N is number of moles, R is the ideal gas constant, and that's a given value that you're just basically going to plug in to the formula. And we get that constant from standard temperature and pressure values. So I can show you in a second how we got that R value. And then T is temperature. So PV is equal to nRT. So that's the last and final equation that we'll use this unit. So the R values, like I said, these are just given values that you're going to plug into the problem. So I'll show you a few examples in a second, but these two you should write down because these are the two most common ones that you'll use. The one value for R, and this is just a constant, remember that you throw in, is 8.31. All of this information is units. So basically, in order to use the 8.31 value, volume has to be in liters, pressure has to be in kPa, moles has to be in moles, and temperature has to be in Kelvin. So you'll want to look at the information from the problem to see what units everything is given in, and then use that to match up the R values. The second R value that you could use is 0.0821, and to use this value, volume would have to be in liters, pressure has to be in ATM, moles has to be in moles, and temperature has to be in Kelvin. So if you notice, pressure is the only difference between these two R values. So if the pressure in the problem is given in kPa, you would use 8.31. If the pressure in the problem is given in ATM, then you would use 0.0821. So let me show you quick where we get these numbers from. So if you remember from last unit with moles and stoichiometry, which I know that you remember because you loved them so much and you loved doing those calculations, when we looked at standard temperature and pressure, standard pressure is either 1 ATM or 101.3 kPa or 760 millimeters of mercury. Standard temperature is 273 Kelvin. And then from the moles and stoichiometry unit, we know that 1 mole of any gas at STP takes up 22.4 liters of space. So again, in order to use this mole value, our temperature and pressure have to be standard. Most of these calculations that we've done this unit, we've been given a different temperature and a different pressure reading. So that's why we can't use this number all the time. You can only use it when the values are at STP. So if you, and again, I just want to show you where we get these numbers from. I'll just do one as an example. If this is your equation, we have standard pressure. So I'll use, just for simplicity, we'll use the 1 ATM. So if you have 1 ATM, times volume, and we know that 1 mole of gas takes up 22.4 liters of space. And then if we're solving for the R value, whoops, I didn't leave myself enough room here. I'm going to move that over and write a little smaller, sorry. Here, we'll put it down here, PV equals nRT. Okay, so if we have 1 ATM and the volume is 22.4 liters, and we're using 1 mole of gas, and we're solving for R, and standard temperature is 273. So again, to show you where we get these R values, I'm just plugging in standard pressure and standard temperature and standard volume. So if we take 1 ATM times 22.4, we get 22.4, and that's liters times ATM. And then if we take 1 times 273, we get 273, and that is moles times Kelvin, and then times our R value. So to get R by itself, we have to divide each side by our 273, and then the unit is moles times Kelvin. So if we take 22.4 divided by 273, whoops, you get 0.08205, and then of course if we round to 3 sig figs, we end up with 0.0821. So we got this number because our pressure value was in ATM. So again, that's where scientists came up with this R value, is by plugging in these standard values. So when you're solving the problem, you are either going to use the ATM value for R or the KPA value for R. So again, I'll show you an example on the next slide that will hopefully make a little more sense. All right, so like we said, ideal gases don't exist, but real gases differ the most from ideal gases at low temperatures, because at low temperatures the particles are not moving as much, and at high pressures. So when you push those molecules together, then they have more differences between real and ideal gases. All right, so we'll go through 2 practice problems just so you can see the ideal gas law being used. So again, we're going to write down the information given in the problem. So we have 34 degrees Celsius, whoops, which is a temperature. So a temperature is 34 degrees Celsius. The pressure inside a nitrogen-filled tennis ball with a volume of, so we have a volume of 0.148 liters, is 212 kPa, which is a pressure. How many moles, so remember moles is N, are in the tennis ball? So one way that we know that we have to use the ideal gas law for this one is that the question asks us about moles. So if the question asks you about moles, PV equals nRT is the only equation that uses moles. The other way that we know is because we're only given 1 temperature and 1 volume and 1 pressure. We're not given 2 temperatures or 2 volumes. So if you're only given 1 of every variable, the only option is PV equals nRT. So then if we plug in our variables, so pressure is 212 kPa times volume, which is 0.148 liters. The number of moles we don't know. Now we have our R value. So remember, our R value is based on pressure. The pressure in this problem is in kPa. So if we go back to this slide, here's our kPa value. So for R, we're going to use 8.31. And again, the liters times kPa over moles times Kelvin, that's just the unit. So we have to have that unit in order for all the other units to cancel out. So we're going to plug in 8.31 and then liters times, whoops, kPa, I almost wrote in the wrong unit, over moles times Kelvin. And then times temperature, which we have to add 273, so this is going to be 307 Kelvin. So then this would be your initial setup. So I'm going to take the left side of the equation and solve for that. So 212 times 0.148, and I'm going to get 31.376 kPa times liters is equal to N, which we don't know, and then 8.31 times 307 is 2,551.17. The only unit that cancels out over here is Kelvin, so we still have liters times kPa over moles. So then to get N by itself, we have to divide each side by 2,551.17. So then all of that cancels out. And then liters cancels out, kPa cancels out, and then we're left with moles, which is what we want. So 31.376 divided by 2051.17, and we get a value of 0.012296. For sig figs, all of our numbers have 3 sig figs. Remember, this leading 0 is not significant. So we would end up with a final value of 0.0123 moles. So that would be your final answer. That would be how many moles of nitrogen gas are in the tennis ball. All right, so let's look at this last problem. Again, we're going to write down what's given. So a child's lung can hold 2.20 liters. So liters is a volume. We want to know how many grams. So we want to know a mass. This will be a tricky one. Of air do her lungs hold at a pressure of 102. So we have a pressure of 102 kPa. And a body temperature of 37 degrees Celsius. All right, and then we have the molar mass of air is 29 grams per mole. So we're only given one pressure, one volume, and one temperature. So we have to use PV equals nRT. But what's tricky here is we want to know how many grams. N is moles, so we can solve for moles, and then we can use the molar mass to convert back to grams. So there's kind of 2 steps to this problem. So anytime the problem asks for moles or grams, you have to use PV equals nRT. All right, so let's plug in our numbers. So pressure is 102 kPa. Times volume, which is 2.20 liters, equals N, which we don't know. The R value, remember we have to go back and look to see which value we're going to use. The pressure in this problem is in kPa. So if we go back, here's our kPa value. So again, we're going to use 8.31 for the value for R. And that's liters times kPa over moles times Kelvin. And then our temperature, we have to convert to Kelvin, which would be 310 Kelvin. Whoops, pen is cutting out here. Okay. So then I'm going to solve the left side of the equation. So 102 times 2.20. Oops, I'm going to use a different color here so we can make sure everything stays separate. And then we have kPa times liters is equal to N, which we don't know. And then I'm going to take 8.31 times 310 to give me 2,576.1. The only unit that cancels out is Kelvin. So I'm going to still end up with liters times kPa over moles. And then to get N by itself, I have to divide each side by 2,576.1 liters times kPa over moles. So that all cancels out. We're going to divide each side by this number. kPa cancels out, liters cancels out, we're left with moles. So our first answer, if we take 224.4 divided by 2576.1, we get 0.087108. I'm going to keep as many numbers as I can because this is moles. We want to know grams. So we have to do one more conversion because we have to convert grams to moles. So remember, whatever unit you start with on top goes on the bottom of the next step. So we know that in 1 mole, the problem tells us here is the mass. So in 1 mole of this gas, there are 29 grams. So moles cancels out, you're left with grams. So you take that big long answer and multiply it by 29, and you get 2.526144, blah, blah, blah. And then for sig figs, we have 3 sig figs throughout. So we're gonna end up with, whoops, my pen works. We're gonna end up with 2.53 grams. So sometimes you do have to do this extra step, not often, but it's kind of a challenge, merging the information that we used last unit to this unit. Don't you just love chemistry? I do. I know you do too. All right, let me know what questions you have.